we have derived the equation for wavelength of de Broglie hypothesis and the wavelengths of protons, electrons and alpha particles. We have already derived the wavelength of electrons. Now we will derive the wavelengths of protons and alpha particle. So, let us consider wavelength of proton is lambda p. So, lambda p is equal to h by root over 2 mp v qp. So, again we will put the values that we know. Into the mass of proton is 1.66 into 10 to the power minus 27 kg into charge of one proton is 1.6 into 10 to the power minus 19 coulomb into V. So, by calculating we get lambda p is equal to approximately 0.286 into 10 to the power minus 10 by root V meters. Again 10 to the power minus 10 meter is equal to 1 angstrom. So, we get lambda p is equal to 0.286 by root V angstrom. Now, we will derive the wavelength of alpha particle. Lambda alpha. Now, what is the mass of alpha particle? Alpha particle is helium with atomic number of 2 and mass number of 4. Right? Therefore, mass of alpha particle will be 4 into 1.66 into 10 to the power minus 27 kg. Since the mass of neutron and proton are considered as almost equal, so we will multiply this value with 4. And the charge of alpha particle will be twice that of the charge of proton. So, 2 into 1.6 into 10 to the power minus 19 coulomb. So, wavelength of alpha particle will be 6.626 into 10 to the power minus 34 joule second. This is Planck's constant divided by 2 into, so if we multiply all together, 2 into 4 into 1.66 into 10 to the power minus 27 kg into 2 into 1.6 into 10 to the power minus 19 coulomb into V, right? By calculation we get lambda alpha is approximately 0.101 into 10 to the power minus 10 by root V meters. Therefore, lambda alpha is equal to 0.101 by root V angstrom. So, we have derived the wavelengths of electron, proton and alpha particle. Now, this was the wavelength of electron, this is the wavelength of proton and this is the wavelength of alpha particle. If we compare wavelength of electron is 12.27 into 1 by root V, right? Wavelength of proton is 0.286 into 1 by root V, and wavelength of alpha particle is 0.101 into 1 by root V. Therefore, this term is common in all these expressions. So, we will see only these quantities. By these quantities we see that lambda of electron is much greater than lambda of proton, and lambda of proton is greater than lambda of alpha particle. Since we know that the dimension of electron is very small as compared to proton, and proton is smaller than alpha particles. So, we had also seen this formula, that in this formula what was there, 2mVq, right? So, lambda is inversely proportional to square root of mass. Therefore, the higher the mass of the particle, the lower will be its electrons. We know that mass of electron is very less than mass of proton, and which is in turn less than the mass of alpha particles. So, the order of wavelength is also matching this order of dimensions. Now, the de Broglie's wavelength had some particular applications. De Broglie's hypothesis that matters like electron, proton or some similar particles have wave-like properties. A very practical example was observed when an electron beam was observed to undergo diffraction. We know that properties like interference and diffraction are the properties of waves. So, when the electron beam underwent diffraction, then it was proved that particles like electrons also possess wave-like properties. A very practical example of the wave nature of electrons is used in electron microscopy. Electron microscopy is a very important tool for advanced scientific research, and electron microscopes provide much higher magnification as compared to ordinary microscopes which use light beams. Now, the fact is that why don't we observe wave-like properties for ordinary objects that we see in daily life? For example, a fast moving ball. The fact is that de Broglie's hypothesis is applicable only for very small objects like the subatomic particles. It is not applicable for macroscopic elements. Why? Because we have seen this relation. Lambda is inversely proportional to the square root of mass. So, when mass is very high, lambda is inversely proportional to square root of mass. So, when mass is very high, lambda will be very small, right? So, when for electrons and protons we have seen that the wavelength is obtained in terms of 10 to the power minus 10 meters, which is in the angstrom scale. And whereas the mass of electrons and protons lie in this range, that is 10 to the power minus 27 or 10 to the power minus 31. Now, for macroscopic elements, what happens? For example, a ball, it has a mass in grams. It has mass in grams. Grams means 10 to the power minus 3 kg. So where is 10 to the power minus 27 kg and where is 10 to the power minus 3 kg? This is very large. So wavelength will be so small that it can be neglected. So wavelength can be negligible. Therefore, wave nature is only applicable for particles like electron, proton, etc. Right? So, we have studied about the de Broglie's hypothesis. Now we will read about the second discovery which led to the failure of Bohr's model. The second discovery was Heisenberg's uncertainty principle. So now we will study Heisenberg's uncertainty principle. This is called HUP. This was discovered in 1927 by Werner Heisenberg. Werner Heisenberg, he was a German physicist. Okay, so what was Heisenberg's uncertainty principle? Heisenberg's uncertainty principle stated that it is impossible to determine the position and momentum of a particle like electron simultaneously. That is, for example, a particle like electron which is very small, for such particles we cannot determine the exact position and exact momentum at the same time, because to determine the position of electrons we need some scale whose dimensions are less than the dimensions of electron. So this is possible by bombarding the electron with light beam. Now the measurement of exact position of electron is possible when the wavelength of light that is striking the electron has a wavelength which is less than the dimension of electron. And when light strikes on electrons, light has particles which are photons. So photons are also very small particles and electrons are also very small particles. So when a light beam strikes on an electron, so there will be a collision between the photons and the electrons, and the energy of the electrons will change due to the collision. And we know that due to collision there is a transfer of energy and transfer of momentum. So simultaneously the momentum will also change, and due to collision the position of electron also becomes uncertain. So Heisenberg's uncertainty principle stated that it is impossible to determine the exact position and exact momentum of an electron or similar particles simultaneously. Okay. So let's say this is the nucleus, this is the orbit, and an electron is here. Now a light beam strikes on the electron. So what will happen? Light beam contains photons. So photons collide with the electron. Now when photons will collide with the electron, then both position and momentum of the electron becomes uncertain, right? So Heisenberg gave this statement. Let's say when the electron is illuminated, with light of wavelength less than the dimension of electron. Now to determine the position of electron accurately, it is very necessary that we illuminate the electron with a light beam whose wavelength is less than the dimension of the electron. By this process, position can be determined. But we know that momentum is equal to h by lambda from de Broglie's hypothesis. So when lambda is very small, momentum will be very large. So if we calculate the position, determination of momentum is not possible. And if we try to determine the velocity or momentum, if we calculate velocity or momentum, then position cannot be determined accurately. So by this, if position of a particle is x, then uncertainty of position is considered to be delta x, and if momentum is p, then uncertainty of momentum is considered delta p. Therefore, Heisenberg proposed this equation that the product of uncertainties of position and momentum is greater than or equal to h by 4 pi. And in this equation, uncertainty was considered in terms of magnitude. This was the statement of Heisenberg's uncertainty principle. In the next lecture, we will study about its significance. Thank you.